Good morning, student. Welcome to our YouTube channel ABA Online Physics. In this lecture, we discussing about the unit and measurement. Here, we covered some points, that is measurement of length, large distance, small distances, then measurement of mass, measurement of time, accuracy, error in measurement, systematics error, random error, absolute error, combinations error, dimension, dimension analysis, etc. So first we discuss here the measurement of length. How to measure the length in order of the distance varies from 10 raised to power minus 14 meter. It means the radius of nuclei to the 10 raised to power 25 meter. That is the radius of universe. Okay. The distance ranging from 10 raised to power minus 5 meter to 10 raised to power 2 meter can be measured by direct method, which involves comparisons of distance or length to be measured with chosen standard length. Now, for examples, a meter rod can be used to measure the distance as small as 10 raised to power minus 3 meter. A vernier calipers can be used to measure as small as distance 10 raised to power minus 4 meter. A screw gauge is used to measure as small as 10 raised to power minus 5 meter. For every small distances or very large distances indicates indirect method are used. So measurement of large distances. How to measure the large distance? The first method, that is parallax method. What is the parallax method, or how to measure the large distance by using this method? So consider far away a planet P at a distance d from our two eyes. Okay, here I take the point P and this is the eyes left and right. Okay, now suppose that line joining the planet to the left eye is L, okay, and right eye is R. The subtended angle theta in radian. Here subtended angle theta. Then the angle theta is called as the parallax angle, okay, or parabolic angle, and distance LR is B, is called the basis. Okay, this distance is B, that is called as a basis. As planet is far away, B by D is greater than 1 and therefore theta is small. Then taking the distance LR is B as the circular arc of radius D, we have theta is equals to this arc LR by radius D. It means this distance is B by D. Is theta is equals to B by D. Therefore, D is equals to B by theta. Means we calculated this distance, this eyes to that planet distance, this D distance is equals to B by theta. This is the parallax method. Now, measurement of size or angular diameter of astronomical object. How to measure? See, this is the planet, this diameter D, and this is the earth. Okay, from the earth to the that planet distance is D, capital D, and here created some angle, that is alpha. If D is the diameter of the planet and alpha is the angular size of the planet, means the angle subtended by D at the earth, then alpha is equals to D small d by capital D. The angle alpha can be measured from the same location on the earth. Now it is the angle between the two direction, when two diametrically opposite points of the planets are viewed through the telescope. Then since D is known, suppose this D is known, then the diameter of D of the planet can be determined from small d is equals to alpha D. Now ecosystem or reflection system. This method is used to measure the distance of hill. See, like this is the gunfire to the hill and a echo sound is received. means a gun fired toward the hill, and the time interval between the instant firing of gun and the instant of hearing the echo of the gun shot is noted. Now, this this is the time taken by the sound travel from the observer to the hill and back to the observer. Okay. If v is the velocity of sound, then s is the distance of the hill from the observer, and t is the total time taken. Then that is distance is equal to v into t by 2. V into t by 2. Estimate of very small distances. First, by using the electronics microscope. For the visible light, the range of wavelength is about 400 Armstrong to 700 Armstrong unit. Actually, 1 Armstrong unit is equals to 10 raised to power minus 10 meter. Here, optical microscope cannot be resolve particle with size smaller than this. Electron beam can be focused by properly design the electric and magnetic fields. The resolution of such electron microscope is limited. Finally, the fact that electron can also behave as a wave. The wavelength of electron can be small as a fraction of an Armstrong. Such electron microscope with resolution of 0.6 Armstrong have been built. They can almost resolve atom and molecule in a material. In recent time, tunneling microscopy has been developed, in which again the limit of resolution is greater than Armstrong. It is possible to estimate sizes of the molecule. Now, the range of length is the range of lengths. The size of object we come across in the universe varies over very wide range. This may vary from size of order 10 raised to power minus 14 meter of the teeny nucleus of an atom to the size of order 10 raised to power 26 meter of the extended of observable universe. We also use certain special lengths unit in short or large distances, which is given below. Here I write units. This is the symbol, value, and this is the definition. First, 1 Fermi is equals, symbol is 1 F, value is 10 raised to power minus 15 meter. 1 Armstrong, that is 10 raised to power minus 10 meter. 1 astronomical unit, that is 1 AU, 1.496 into 10 raised to power 11 meter. Definition, average distance of the sun from the earth. Now 1 light year means the value is 9.46 into 10 raised to power 15 meter. The distance of light travel with the speed of light 3 into 10 raised to power 8 meter per second in 1 year. 1 parsecond value is 3.08 into 10 raised to power 16 meter. The distance at which average radius of the earth orbit suspended an angle of 1 arc second. Then range and order of length. Here I given size of the object or distances and length in meter. So size of proton 10 raised to power minus 15 meter. Size of the atomic nuclei 10 raised to power minus 14 meter. Size of the hydrogen atom 10 raised to power minus 10 meter. Length of typical virus 10 raised to power minus 8 meter. See, like that, here I given the size of object or distances in meter. Now the measurement of mass. How to measure the mass? The SI unit of mass is kg, that is kilogram. Now a prototype of the international standard kilogram supplied by the International Bureau of Weight and Measure, that is BIPM, are available in many other laboratories of different countries. In India, this is available in National Physical Laboratory, that is NPL Delhi, New Delhi. While dealing with atoms or atom and molecule, the kilogram is in an convenient unit. In this case, there is an important standard of mass called Unified Atomic Mass Unit, that is AMU, which has been established expressing the mass of an atom as 1 atomic unit is equal to 1 U. One undefined mass unit is equal to 1 by 12th of the mass of the carbon C12. Isotopes is 12C6 including the mass of electron. Means 1 U is equals to 1.66 into 10 raised to power minus 27 kg. Methods of measuring mass. First, by using the common balance. Second one, large masses in the universe like planet, star, etc. based on the Newton's law of gravitation can be measured by using gravitational method. Third one, measurement of small masses, that is atomic, subatomic particle, etc. We can use the mass spectrograph in which radius of the trajectory is proportional to the mass of the charged particle moving in a uniform electric and magnetic field. Then range of masses. The masses of objects we can across the universe vary over a very wide range. This may vary from teeny masses order 10 raised to power minus 30 kg of an electron to hug mass of about 10 raised to power 55 kg of the known universe. The range and order of masses, object and masses. Electron 10 raised to power minus 30 kg, proton 10 raised to power minus 27 kg, uranium atom 10 raised to power minus 25 kg, red blood cell 10 raised to power minus 13 kg, dust particle 10 raised to power minus 9 kg, mosquito, grapes, human, automobile, etc. Moon 10 raised to power 23 kg, earth 10 raised to power 25 kg, sun 10 raised to power 30 kg, like that. Measurement of time. How to measure the time? We use the atomic standard unit, which is based on the periodic vibration produces in cesium atom. This is based on cesium clock, sometimes called atomic clock, used in national standard. In cesium atomic clock, the second is taken the time needed for 9,192,631,770 vibrations of the radiation corresponding to transition between the two specific hyperfine levels of the ground state cesium-133 atom. The vibration of cesium atom regulate the rate of cesium atomic clock just as the vibration of balance wheel regulate an ordinary wristwatch or the vibration of small quartz crystal regulate a quartz. Now, a cesium atomic clock used in National Physical Laboratory NPL, New Delhi to maintain the Indian Standard Time. Then range and order of time interval. Here the time largest one is 10 raised to power 41 to shortest one. Here lifespan most unstable particle 10 raised to power minus 24 second, that is period of X-ray 10 raised to power minus 19 second, period of atomic vibration 10 raised to power minus 50 meter. See, like that, this is the time interval in second. Then accuracy, precision of measurement instrument and error in measurement. First, what is meant by error? The result of every instrument by a measuring instrument contains some uncertainty. This uncertainty is called error. Accuracy, what is meant by accuracy? How to define the accuracy? The accuracy of measurement is measure of how close the measured value is to be true value of the quantity, that is called as the accuracy. Precision tells used to what resolution or limit of quantity is measured. For example, suppose the true value of the certain length is near 2.874 centimeter. Then in one experiment using the measuring instrument resolution 0.1 centimeter, the measured value is found to be 2.7 centimeter. while another experiment using measuring device greater than resolution value, say 0.01 centimeter, the length is determined to be 2.69 centimeter. The first measurement has more accuracy because it is closer to true value but less precision. Its resolution is only 0.1 centimeter, while the second measurement is less accurate but more precise. In general, the error in measurement can be broadly classified systematic error and random error. First, we define the systematic error. What is meant by systematic error? The systematic error are those error that tends to be in one direction, either positive or negative. Some of the sources of systematic error. First, instrumental error. The instrumental error that arise from the error due to imperfect design or calibration of the measuring instrument, zero error in an instrument, etc. This is called as the instrumental error. For example, the temperature of graduation of thermometer may be inadequately calibrated. It may be 104 degrees Celsius, the boiling point of water at STP, whereas the should be read 100 degrees Celsius. Or in vernier caliper, the zero mark of vernier scale may be not coincide with zero mark of the main scale. An ordinary meter scale may be one off at one end. These are the examples of instrumental error. Now, imperfection in experimental technique or procedure to determine the temperature of human body. A thermometer placed under the armpit will always give the temperature lower than actual value of the body temperature. Third one, that is personal error. The personal error arises due to individual bias, lack of proper setting of the apparatus, and individual carelessness in taking the observation without observing proper precautions, etc. For example, if you hold your head a bit too far right while reading the position of needle on the scale, you will introduce an error due to the parallax. Systematic error can be minimized by first improving experimental technique, second selecting better instruments, and third one removing personal bias as far as possible. By using this we can minimize the systematic error. Now the random error. What is meant by random error or how to define the random error? The random error are those errors which occur irregularly and hence are random with respect to sign and size. This can be arise due to the random and unpredictable fluctuation in experimental condition, personal error by observing, taking readings, etc. For example, when some person repeat the same observation, it is very likely that he may get different readings every time. Then list count error. List count. First, list count. The smallest value can be measured by measuring instrument is called as the list count. What is the list count? The smallest value can be measured by using by the measuring instrument is called as the list count. The list count error is an error associated with resolution of an instrument. For example, a vernier caliper has list count as 0.01 centimeter. A spectrometer may have list count 0.001 centimeter. Using the instrument of higher precision, improving experimental technique, etc., we can reduce the list count error. Repeat the observation several times and taking the arithmetic means of all the observation. The mean value will be very close to the true value measured quantity of the measured quantity. Note some point to be noted. The list count error belong to the random error category, but with a limited size. It occurs with both systematic and random errors. Then absolute error, relative error and percentage error. What is meant by absolute error, or how to define the absolute error? The magnitude of difference between the individual measurement value and true value of the quantity is called as the absolute error of the method. It is denoted by delta A, mod of delta A. Note, in the absence of any other methods of knowing the true value, we consider the arithmetic mean as the true value. The error in the individual measurement value from the true value are, that is delta A1 is equals to A1 minus A mean, or delta A2 is equals to A2 minus A mean. Now delta AN is equals to AN minus A mean. The delta A calculated above may be positive or negative, but absolutely error mod of delta A always be positive. The arithmetic mean of all the absolute error taken as find or mean, the final or mean absolute error, the value of physical quantity is A. It is represented by delta A mean. Thus, delta A mean is equals to mod of delta A1 plus mod of delta A2 plus mod of delta A3 up to mod of delta AN divided by N. It means summation I is equal to 1 up to AN mod of delta AI by N. If we do a single measurement, the value we get may be in the range delta A mean plus minus delta A mean. This implies that all the measurements of physical quantity A is lie between A mean plus delta A mean and A mean minus delta A mean. Then relative error. The relative error is the ratio of mean absolute error, that is delta A mean, to the mean value A mean of the quantity measured. Means relative error is equals to mean absolute error by true value or arithmetic mean. The relative error is equals to delta A mean by A mean. Then percentage error. When the relative error is expressed in percentage, it is called as the percentage, that is the delta A, small delta I. Then percentage error, mean absolute error by true value or arithmetic mean into 100. Then percentage error, that is delta A is equal to delta A mean by A mean into 100. This is called as the percentage error. Up to this we will stop here. In next lecture we discuss about the errors, means that is the different types of error, different combinations of error, dimension, how to find the dimension of standard quantity. Okay.